Hi, Pranit. I am audible, right? Can you confirm once?
Yeah, Gaurav, yeah, you're audible.
Okay. Uh, no one else has joined.
The professor are going to arrive soon.
Sorry. Okay, just to confirm, you are a core student or you are from NPTEL team? Hello, Pranit. Pranit, are you there? Hello. Hi, Sahil. Okay, so I think we can get started with the session. Since it's live, the students who are not attending can later get through the recorded video. So let me just share my screen. I'll start with the week 8 assignment question. Just give me a minute. I will share my screen. Okay, so both week 8 and week 9 assignments were based on max flow and min cut. So I plan to take both of the questions together in today's session. So let's just get started with this week 8 problem. So the problem is you are assigned to allocate classrooms to courses and you are given n courses numbered from 1 to n, and each of the course has the number of students who are registered in that course. So you are also given an array where AI denotes the number of students who are registered in the course, ith course. And you're also given m classrooms numbered from 1 to m, and you are given an array B, where Bi represents the capacity of the classroom, ith classroom. And basically your task is to assign each of the classroom to one of the courses. So there are two conditions. Each course can be assigned to exactly one classroom, at max one classroom, and one classroom can be assigned to at max one course. And the additional condition is that suppose we assign the classroom I for the course J, then we need to, this is only possible when the capacity of classroom I is greater than or equals to the number of students registered in the course, Jth course. Right? So these are the conditions. So Sahil, would you like to share your approach if you had solved this problem? Or okay, I'll just go ahead with the solution that I had thought in my mind. So we are given these courses and these classrooms, and there are these two conditions, right, that I just explained. So each classroom RJ can be allotted to exactly one course CI and vice versa. And if classroom RJ is being allotted to course CI, it is only if it has sufficient capacity. That means BJ should be greater than or equals to AI. So if you observe, this whole problem boils down to the problem of maximum matching. How? So let's just divide this, construct this bipartite graph where one of the partition is classrooms and the other partition is courses. So I'm just using, okay, sir, I'm using my Samsung notes just to make this session more easy. Yeah, sure. Okay, no problem. Let's continue on the topic. So there are m classrooms, so there will be m vertices in this first partition. There are n courses, so there will be n vertices in this second partition. And how will I construct the edges between these two partitions will depend on the last condition, which is if the jth course, jth classroom RJ has the capacity to accommodate students of the course CI. That means BJ is greater than or equals to AI. Then I will add an edge between RJ and CI. This is for all vertices of classrooms partition and all vertices of courses partition. So all the pairs RJ comma CI. So there will be total of n times n pairs. I will check if BJ is greater than or equals to AI. If that is true, I will add the edge, right? So at max, there can be m times n edges between these two partitions. And now, if you observe, this problem is simply finding a maximum matching of this bipartite graph, right? Because we just want to allocate each classroom to exactly one course and each course to exactly one classroom, and that is basically what is what the maximum matching problem says. So you can use any approach for finding the maximum matching, but I emphasized making a flow-based approach just to make sure that you understand how to implement the fault Fulkerson or any other flow-based algorithm. So I will just go ahead with the flow-based approach. How can we solve this maximum matching using flow-based approaches? You add two additional vertices, one S and one T. S is the source vertex and T is the terminal, this sink vertex, right? And you need to add these additional edges from source to each vertex of the first partition and from the vertices of each vertex of the second partition to the sink. These additional edges and these two vertices S and T are, I have added it in the graph. And now for the flow, we have identified source and sink. What remaining is the edge capacities, right? Now, how should we assign the edge capacities? Can anyone want to answer the question? What are the capacities of each of these edges? So these are type 1 edges, these are type 2 edges, and these are type 3 edges. So what will the capacity of type 1 edges, type 2 edges, and type 3 edges? We want to find the maximum flow, maximum matching from between classrooms and courses, for which we have constructed this flow graph, and in which we have assigned the source and sink vertex. Just the edge capacities are remaining. Can anyone tell what will be the core, the edge capacities? Okay, let me just go ahead with it. So observe that we want to capture the maximum matching in this particular bipartite graph, right? So if I identify this edge in the maximum matching, then this vertex should not occur in any other edge, right? I should not take this edge in account for the matching, because this vertex has already been considered in this edge. So for that, what we can do is we can give each of this edge a capacity value of 1. So if you observe, this vertex is receiving at max flow of 1. So only flow of 1 can go out of it, right? So this will ensure that this whatever edges are which is coming as an answer of the maximum flow will its endpoints will be connected to only one of the edges of this bipartisan. This will be answered by putting edge capacities as 1 here. And similarly for sink vertices also, to ensure that this vertices has exactly these vertices are connected with exactly one vertex of this classroom partition, the edge capacities will be 1, because you only want to have a flow of 1 from these vertices as well as these vertices. Now for the type 2 edges, means these edges, it doesn't matter what value of flow you put, because you have already uh, uh, ensured the maximum flow which can go out of S and the maximum flow which can come into the sink. So you can just initialize all these edge capacities as 1, and this will and the maximum flow from this whole constructed flow graph will give you the maximum matching. So basically the edge capacities of all the edges, I'm giving it a value of 1, and that will work for finding the maximum matching, right? So this is the whole problem, and this all edge capacities will be 1, and now the thing just remaining is the implementation of the flow. So how will you implement the flow algorithm? I will show what I have implemented. Let me just give me a second. I will show you my implementation. Okay, so I implemented a fold recursion algorithm to find the maximum flow. So if I have, so first NMN are the this number of courses and number of classrooms. A is the capacity. Is the students number of students registered in all the courses. This is the array. B is also array, and I'm representing the graph as adjacency matrix. So the total number of vertices will be the number of courses plus the number of students. The number of classrooms plus the source vertex plus the sink vertex. So n plus m plus 2 additional vertices, which is source and S and T, source and sink vertices. So the total number of vertices in this graph will be n plus m plus 2. So I'm creating an adjacency matrix of size n plus m plus 2 cross n plus m plus 2. Now this for loop will add the edges from the source vertex to the partition of the first partition. So I'm going from 1 to n plus 1. So the vertices number from 1 to n plus 1 represents the first partition, and vertex 0 is the source vertex. So from the source vertex to the vertices of the first partition, I'm initializing the edge capacity as 1. Now the n plus m plus 1th vertex is the sink vertex. This is the last vertex. Since it is zero indexing, the last vertex will be n plus m plus 1. And the first partition was 1 to n plus 1, and the second partition is from n plus 1 to n plus m plus 1, right? So I am adding an edge capacity of 1 from the vertices, all the vertices of the second partition to the sink vertex. So this will initialize the edge capacities uh, for the third type of edges, right? And now we are remaining with the middle edges. So while adding the middle edges, you need to consider the condition that was mentioned in the question, that if you are adding a edge between particular classroom and a class and a course, that classroom should have enough capacity to ensure that all the students can sit there, right? So I'm iterating through each of these courses from 1 to n plus 1. Then I'm iterating from each of the classroom n plus 1 to n plus m plus 1. And if the number of registered students in this particular course is less than or equal to the capacity of this particular classroom, then only I will add this age, and its capacity value is 1. So basically, this, why am I using adjacency matrix is, whenever the value of I comma j is 0, that means there is no edge between the vertex I and j. And normally, if the value of I comma j is 1, it represents that there is an edge between vertex I and j. But I'm using that particular value also as an edge capacity. So I can use here, instead of 1, I can put 2 or 3 also. This will represent that there is edge between vertex I and j, and it has a capacity of 3. So I can represent an edge with capacity using this adjacency matrix, right? So that's why I have preferred adjacency matrix over adjacency list for this particular problem. And now this is just the implementation of fold percussion. So it uses a BFS for finding the augmented paths. So BFS, I'm initializing a queue with the vertex S. I'm initializing a visited array. And while the length of queue is not 0, I will I will take out the first element from the queue. Then I will go over all the other vertices, and I will see if that vertex, that there is an edge between vertex U and I, and it has a positive capacity, means flow can be transferred through that edge, and that vertex is not visited yet. Then I will add it to the BFS queue, and I will mark it as visited. What this parent array will do is, so I am finding the augmented path. After finding the augmented path, I will need to also find the bottleneck edge on that augmented path, right? Because to know what value of flow will pass through that augmented path will really depend on the bottleneck edge. And the bottleneck edge is the edge which has the lowest capacity on that augmenting path. So for that, I'm maintaining this parent array so that I can traverse back from the vertices which has been added to the queue, right? And if in the augmenting path, I'm starting from the source vertex. If I reach that sink vertex T, then I will return true, and this will return an augmented path. And if I'm not reaching to the sink vertex by traversing to the queue, that means all the augmenting paths have been already enumerated. So I will just return false. Now, what this fold percussion algorithm will do, it will initialize the parent array with -1, or initialize max flow with 0, until there is a augmenting path. That means until there is a path which goes from S to T and has a positive capacity, like positive flow can pass through that path. I initialize a temporary flow with a bottleneck edge value with, that will be the flow value that pass through that augmented path. So I initialize the bottleneck edge value with infinity. And now I am at node T, and using this parent array, I will traverse back to the vertices which has been visited before this parent array. So I started from the vertex S, right? So I will traverse back until I reach the vertex S. And I will update the value of bottleneck flow with the minimum value of the previous flow, and the edge capacity from the parent parent node of this particular vertex and this vertex. So we uh, so assume we have an augmented path that goes from vertex 1 to 2 and then 3, where 1 is the source vertex, 3 is the sink vertex, and the path, the intermediate vertices are 2. So 1, 2, and 3, it is a path. So I'm at the, so the parent of 3 will be 2, parent of 2 will be 1. So currently I'm at vertex 3, and this, what this will return is adjacency matrix of parent of 3 is 2, and this is 3. So what is the capacity of the edge which goes from vertex 2 to vertex 3? So this will be the last edge in the augmenting path. And similarly, in the second iteration, what it will check what is the capacity of the edge which goes from the vertex 1 to vertex 2. And whichever edge has the minimum capacity, the flow that will be saved in that this variable flow. And this will be the our bottleneck capacity of that particular augmenting path. And now we'll update the flow value with that bottleneck capacity. Right, so we have updated the flow value, but still one thing is remaining, that is the residual edge capacities as well as the normal edge capacities, right? So we are assuming that we are passing a flow from this particular augmented path which is written by BFS. Since we are passing this flow, we need to update the capacities. So what we'll do, we'll again use the parent array. So we are at the vertex T sink. U is the vertex which is parent of this which is parent of T. Basically, if you consider the earlier example 1, 2, 3, the path goes from 1 to 2 to 3. So the parent of 3 will be 2. So we are considering the vertex, the edge from 2 to 3. Since we augmented a flow of value this particular variable, we will subtract the capacity of this edge, and this is the reverse edge. This is the residual edge. So the edge from 3 to 2, we the residual edge, since we are passing a flow of value flow, we will need to add this value to the original capacity of the residual edge, right, which was originally 0. So the edge capacities of residual edge are initialized with 0, and whenever we are we are passing a flow of value f from augmented path, we will add this flow to the residual edges. And so this while loop will update the capacities of all the edges as well as residual edges. And this is the overall implementation of the problem, right? Is there any doubt in this particular implementation or anywhere in the this week 8 problem? If not, then I will just go ahead with the week 9 problem. Okay, no doubt. Good. So I will share another. Let's just go through the week 9 question. So week 9 question is based on a disjoint path cover, which is a particular property of the mean cut max flow problem, right? So let's first understand what is a disjoint path cover. So consider this particular graph. This is a directed graph. So the disjoint path cover is basically is a set of directed paths which covers all the vertices of the graph. And the additional condition is these paths are disjoint. So no edges or vertices are repeating in this path. So one of the example of disjoint path cover for this particular graph will be, so we can consider this as a path 1, 2, 3 to 6 to 8. Then another path will be 2, 4, 7. And this 5 we can take as the isolated vertex. So these 3 paths, 1, 2, 4, 7, 1. Sorry, this 1 has been already visited. So we'll do 3, 6, 8. Yeah. 3, 6, 8, and 5. So this is a example of 3 cover. So I'm using 3 directed paths to cover all the vertices of this graph. So this graph has a 3 disjoint path cover, right? So it has a disjoint path cover with 3 paths, which has 3 paths. And let's read what the question was about. So a path cover of a directed graph G is a collection of directed paths in G such that every vertex of G lies on at least one path. Similarly, a disjoint path cover of G is a path cover such that every vertex on G lies on exactly one path. So the vertex should not repeat. Once a vertex, say one has appeared on this path, this vertex should not come on any other considered path. So this is a property of disjoint path cover, right? Any doubt in the understanding of disjoint path cover?
No, sir.
No? Okay, that's fine. So I also included one question based on disjoint path cover in the quiz also. So if you see, the last 2 questions of the quiz were based on these disjoint path covers. And that was just so that you can understand what, you can just get started with what structure of the flow you should implement for solving this problem, right? Because coming up with a flow structure is the main thing in all of these in the problems of week 8 and week 9. If you come up with a flow structure which solves this problem, then the remaining question is just the implementation part, right? So that's why I included in it both quiz as well as the programming assignment. So you can approach it theoretically in the quiz and programmatically in this assignment, right? So now the question is, you are given a specifically directed acyclic graph. So observe that the input graph is acyclic. So you are given a directed acyclic graph as input, and your task is to identify the graph has a disjoint path curve of size at max k. And means all the vertices of G can be covered by at max k disjoint paths. If that is possible, it should output yes. And if there is no at max k size disjoint path cover, then the output should be no. Right now, did anyone come up with a flow structure or would like to explain their approach for solving this problem? It's fine if it's not correct or wrong answers are also fine. You can just go ahead with your approach and we'll solve it together. Anyone? Okay, let me just share my approach. So the observation you need to do is, which was also part of the quiz question, is if directed acyclic graph has a disjoint path cover of size at max k, right? This double implies with the fact that I will construct a new graph, which is, so how will I construct this new graph is, for each directed edge u to v, which belongs to edge set of G, I will add 2 additional vertices, u1, u2 for u, 2 additional vertices, v1, v2 for v, and I will add an undirected edge from u1 to v2. Right? This is the G prime. So the number of vertices in G prime is 2 times the number of vertices in G, right? Because for all u belongs to vertex set of G, I am adding u1 and u2 to vertex set of G prime. And for all h uv belongs to edge set of G, I am adding an edge from u1 to v2, and it is undirected edge in the graph G prime. So in this new graph, the number of vertices will be 2 times the number of vertices in original graph, but the number of edges will be same as the number of edges which are in the original graph. Just the difference is in this graph, the edges will be undirected, right? And this construction was already actually given in the quiz question. So The only thing I wanted you all to observe was this observation. See, the directed acyclic graph has a disjoint path curve of size at max k. Then it also implies that this new constructed graph G prime has a maximum matching of size V minus k, where V is the number of vertices in the original graph, right? And this goes for both sides. If G prime has a maximum matching of size V minus k, then the input original graph has a directed path, distant path curve of size at max k. So instead of what we can do is, instead of solving this problem, we can solve this problem. And if this problem returns a yes as answer, then the answer for this problem is also yes, right? Because this implication is for both sides. So this was the main observation. And yes, Santosh, you have any question?
No, sir.
Okay, no problem. So can anyone tell how we can prove this observation? So I just written this statement, but you also need to prove it, right? We need to. So how can we go ahead with proving this particular observation? Did anyone tried, or you can just think of it for a minute and tell about what you are thinking should be the approach for proving this particular fact. So think for some time how we can go prove this particular fact. Okay, so anyone want to tell, or like if you got some idea, any direction is fine. Either you want to prove from this to this or this to this, any direction is fine. We anyway want to prove both of these directions, so we'll go one by one. So any suggestions or minute observations that you think will help in proving this fact? Okay, let me just go ahead with the proof. So first we'll do the forward direction. So we are given a graph G, and we know that it has a disjoint path cover of size, let's say K, right? And let's say P is the set of disjoint path cover, right? So P contains the paths, K paths, K disjoint paths, which covers all the vertices. So it will look like. So these are K paths. All of them are disjoint, and basically combinedly all of them are covering all the vertices of the graph. So the total number of vertices in the graph is let's say Vg equals to n, right? So the graph has n vertices, original graph, and no vertex is repeating in this set because these are disjoint paths. So the total number of vertices in this particular set will be also equal to n. And if you observe, the in degree of any vertex is at max 1. So for this vertex of the path, the starting vertex of the path, the in degree is 0. And for any intermediate vertex or the last vertex, the in degree will be 1 because it has only one incoming edge, right? And same for the out degree. All the vertex will have at max 1 out degree. So vertex which is the ending vertex will have out degree 0, and all other vertices of the path will have out degree 1, right? So Now assume there is a edge from let's take one of the path of this path cover. So say this is a path A to B to C, right? Now for in G prime, this vertex A will get split into two vertices, A1, A2. This B will also get split into vertices, B1, B2, and C will also get split into vertices, C1, C2. And H from A to B will be as H from A1 to B2, B to C will be B1 to C2, right? So this is how the construction of G prime was done. So for each vertex, we represent it as two vertices, A1, A2, B1, B2, C1, C2. If there is a directed edge from A to B, then we'll add undirected edge from A1 to B2. There is a directed edge from B to C. We will add an undirected edge from B1 to C2, right? Now, if you see, there are two edges in this particular path. And this for this particular path, it has two edges. And these two edges, this G prime also has two edges if you consider only these vertices, right? And we can consider it as a matching, right? This both edges as a matching because there are no overlapping vertices in these two edges. Why there is no overlapping vertex? Because the vertex A or B or C has at max 1 in degree, right? That means this vertex A2, B2 or C2 can have at max 1 edge. It can be connected with at max 1 edge because the vertices of path has at max 1 in degree. And similarly, since vertices of path has at max 1 out degree, these vertices A1, B1 and C1 can be connected to at max 1 edge. So I'm not considering the other edges of the graphs that there will be other edges also apart from this path, but I'm only emphasizing on these two edges which were translated from these two edges of the path. So we can add this edge in our matching, right? So this path was of length 2 and this gave us a matching of size 2, right? And for there are total k number of paths. On all of these paths in this path cover will give us some individual matching, and this matching will be disjoint because these paths are disjoint, right? So through this approach, the size of the matching will be same as the number of edges in this whole disjoint path cover, right? Because we are getting the matching of size exactly the length of path for each of these paths. So the overall size of this matching will be the number of the sum of the length of all the paths, which is basically the number of edges in this particular path cover. And what will the number of edges? Can anyone tell? What will the overall number of edges in a K path cover? So if you observe, the vertices has either 1 in degree or 0 in degree. The 0 in degree vertices are the starting vertices. So if there are K paths, there will be K vertices which has 0 in degree. All other vertices which has exactly 1 in degree. So there are total n vertices, out of which K vertices has 0 in degree and n vertices has 1 in degree. And 1 in degree indicates there is a edge, right? So there are n minus K vertices which has 1 in degree, and each of them will represents a unique edge. So the total number of edges in this particular K path cover will be exactly equal to n minus K. And so in this new graph G prime, we will get a maximum matching of size exactly equal to n minus K. So what did we prove? So we had a K size disjoint path cover in graph G. And we proved that there exists a n minus K size maximum matching in this new graph G prime. So this was all about the forward direction. So any doubt in this forward direction?
No, sir.
No? Good. Right. So Now let's prove the other one, the other side, the reverse direction. So now what you want to prove is we are given the graph G prime. So in this the constructed new graph, we are given that it has a maximum matching of size n minus k, and we want to prove that the original graph G has disjoint path cover of size k. So to prove this, what we can do is, so there are two types of vertices in G prime, type 1 and type 2. So each vertex in G was split into vertex, right? U1 and U2. So here by type 1, I mean all the vertices of type U1, V1, A1, like that. And this U2, V2, A2 will go into this type 2 vertices. So these are all the type 1 vertices. Let's suppose there were 4 vertices, A, B, C, D. So in this new graph G prime, it will be split in, all of those 4 will split into 2 vertices, A1, A2, B1, B2, C1, C2, D1, D2. And the crucial observation is there is no edge between any vertices of type 1, and there is no edge between any vertices of type 2. Why? Because for every U to V edge in G, we added edge from U1 to V2 in G prime. So we never added an edge from 2 vertices of the same type. We added a edge from type 1 to type 2. That is undirected edge. But we never added an edge which goes from type 1 to type 1 or type 2 to type 2. That means the vertices A1, B1, C1, D1 will not have any edge in between them. And similarly, A2, B2, C2, D2 will not have any edge in between them. So basically, we got a bipartite graph here in which the first partition is type 1 vertices and the second partition is type 2 vertices, right? And there will be some edges which goes from type 1 to type 2. So let's say there might be edge from A1 to B2, B1 to C2, C1 to D2, D1 to A2, like that, right? Because we added edge from type 1 between type 1 and type 2 vertices, so there will be some edges between these two partitions. And what we are given is there is a matching of size k, sorry, n minus k in this particular graph, right? So we are given that there is a matching of size n minus k in this particular graph. So what we can do is, and this matching will consist of the vertices of the type U1 to V2. So this type of edges are in this matching because as we earlier saw, there are no edges from similar type of vertices. So there is no edge from type 1 to type 1 or type 2 to type 2. There are only edges from between type 1 and type 2. So all of these matching edges will be of the form U1 to V2, right? Now, so let's say the matching edges are in the form of U1 to V2. So let's say A1 to B2, B1 to C2, C1 to D2, and D1 to A2, right? So for what we'll do is, for each of the edges of this type, in the graph G, I will consider this particular edge, U to V. So this U1 to V2, it represents there is a directed edge from U to V in the graph G, right? So the disjoint path cover that I want to find in G, I will consider all the edges of type U to V, where the edge from U1 to V2 belongs to matching edge in graph G prime. So I'll take all the matching, the edges in the maximum matching of graph G prime, which are of the type U1 to V2, and I will consider the edge, directed edge from U to V in the original graph, and I will add it in the the disjoint path curve of G, right? So I don't know what is the actual path, but I'm just adding this edge, and I'm telling that this edge will be part of one of the paths of this directed path cover, right? So now the first thing we need to show is this is disjoint. And the second thing we need to show is the size of the directed path curve of G is at max K. So disjoint is clear. Why? Because see, when will this disjoint property get violated? Then there is a H from U to V and there is also H from U to W, right? This will violate the disjoint property. But can it happen? So suppose that is the case, then in the G prime, what we can say is there is a H from U1 to V2 and there is a H from U1 to W2, and both of these edges are part of the maximum matching. But this will contradict that this is a matching because vertex U1 is appearing on two edges. So this is not a matching. So due to this contradiction, the vertices of the edges that we added in the original, the disjoint path cover from U to V, this will represent a disjoint vertex, union of disjoint vertices, right? Because of this contradiction. So since the maximum matching has a disjoint vertices, this will transliterate also to the disjoint path code that all the edges that we are adding, the vertices will not repeat and all the vertices will be unique. So the if there is a edge from U to V, there won't be any edge from U to other vertex. So this won't occur due to this particular property. So this will ensure that the vertex, any vertex which will appear on at max one path. So so this is a half proof. Actually, what this will ensure is any vertex will have out degree at max one. We only proved that any vertex will have out degree at max one because I'm only considering U to V and U to other vertex. Let's say other case where it might also happen, right? There is a edge from U to V and there is a edge from W to V. This will also violate the disjoint property, right? But again, with the similar thing, if this happens, we can see that in the graph G prime, there is edge from U to U1 to V2 and W1 to V2, which violates the matching property that this edge, this both edge cannot be in the matching at the same time because V2 occurs on both of them. So this will also not happen. So this case doesn't happen. That means for any vertex has in degree at max 1 in G. So what I proved is this vertex, which we are considering in disjoint path cover of G, any vertex has out degree at max 1 as well as in degree at max 1. So we are considering a set of edges, that means a subgraph in which every vertex has in degree and out degree both has at max 1, right? So what this will represent the set of paths, right? Let's consider this particular path. This vertex has out degree 1. Can I add other edge from this vertex? No, right? Because we have already proved this any vertex can add out degree at max 1. This vertex also has out degree at max 1. Can I add another edge? No, right? Because it has out degree at max 1. Similarly, can I add another edge from this to this? No, right? Because this is not possible, right? Because this vertex is in degree at max 1 and this vertex is out degree at max 1. So this is also not possible. So this particular set that they constructed, the disjoint path curve of G, represents a set of path with disjoint vertices. Right? That comes from these two particular facts, that each vertex will have in degree at max 1 and out degree at max 1, which means this set is comprised of disjoint paths. Now, the second thing we want to prove is the number of paths, disjoint paths in this particular set. So let's assume the number of paths is this, the size of the set P, right? And what we know is the size of the matching is K. then how will we compute the number of paths in this disjoint path cover? Any idea? Anyone? Just think about for some time. If you come up with some suggestion or idea, how will we come and how can we find the maximum basically the number of paths in the set that we have constructed? Think about what will be the total number of edges in this set. So you assume that there are total number of this many paths, right? There are total number of this many paths, and what we know is so the total number of edges in this path in this set will be same as the maximum matching, right? Because for each edge in the maximum matching, we added a directed edge in this particular set disjoint path cover. So total number of edges in this set will be the size of matching, which is n minus k, right? And what is the number of edges with respect to total number of paths? So there are total, how many vertices are there? N, right? And if the size of this disjoint path cover is p, we know that there are p vertices. There are p vertices which has in degree 0. That means which doesn't have any incoming edge. And there are these remaining vertices. How many remaining vertices? N minus p. These remaining vertices, each of them has 1 in degree, exactly 1 in degree. That means each of them is connected with 1 incoming edge. And thus the number of total edges in this particular setup will be exactly n minus p, because this n minus p vertices has exactly 1 in degree, and each of them represents the 1 unique edge. And we also know that the total number of vertices, so total number of edges is exactly same as the matching, the size of matching, which is n minus k, which is given in the statement. And so since these two are equal, and we'll cut out, and we'll get that the total number of disjoint paths will be exactly k in the original graph. So this is the overall proof for the reverse direction. So the last part, the total number of paths, is not trivial. So you need to think about it for some time, how I came up with this argument. So basically what I did is, I know that the total number of edges in this graph is n minus k, because the size of maximum matching is n minus k. Now I also want to represent the total number of edges in terms of total number of disjoint paths. So if there are p paths, then I know that there will be p vertices which has in degree 0, right? And the remaining vertices are n minus p vertices. Each of them has a unique incoming edge. So I can also represent the total number of edges in this particular set as n minus p. And this will say that the total number of paths are exactly equal to k, right? So any doubt in this particular proof?
No, sir.
Right. Excellent. So this is the overall setup. Now, the problem here also boils down to the maximum matching. So what we need to do is, we just need to construct this graph G prime and need to find the maximum matching. If the maximum matching, there exists a maximum matching of size p minus k, will output yes. And if there doesn't exist maximum matching of size at least p minus k, will output no, right? So that is the problem now. So first thing is, we are given G. What we'll do? We'll construct G prime. and we'll find a maximum matching. For that maximum matching, we can use the same implementation that we used in the earlier week 8 problem, right? I'll just went through the implementation that I have done. Give me a second. So N is the number of vertices, M is the total number of edges, and K is the input parameter. And we want to know if there exists a K size decision path, at max K size decision path or not. Since I want to use flow-based approach, here also I'm maintaining the adjacency matrix, because in adjacency matrix, as I said, I can represent each cell in this matrix as the edge capacity. So what I did is, so there are n vertices, and what we saw was in the graph G prime, there were 2n vertices, right? The number of vertices are twice as of the original graph. So these are 2n vertices and plus 2 additional vertices for as a source and sink vertex, because we want to find solve the maximum matching problem. So we need to add 2 additional vertices, source and sink vertex. So that's why the adjacency matrix has size of 2n plus 2 cross 2n plus 2. Now the zeroth vertex is a source vertex, and the vertices from 1 to n plus 1 are the type 1 vertices. So I'll add an edge of capacity 1 from source vertex to all the vertices of type 1. Now vertices from n plus 1 to 2n plus 1 are the type 2 vertices, and the 2n plus 1th vertex, which is the last vertex, is the sink vertex. So I will add an edge from each of the vertex of type 2 to the sink vertex with capacity 1. And now for the middle edges in the graph G prime, so we considered, so there is an edge from U to V. So UV is the edge, and I will need to take a vertex of type U1. So what I need to do is I need to add an edge from U1 to V2, right? So in G, there is the edge from U to V. There will be edge from U1 to V2 in G prime. And so U1 is in the type 1 partition. So it will be same as U, but V2 is in the type 2 partition, and type 2 partition is from N1 to 2n plus 1. So I need to add the offset of N, V plus N to represent. So vertex V represents the type V1, and vertex V plus N represent the V2, type 2 partition. So I have made an offset of N between type 1 and type 2 partition. So basically 0 is the source vertex, 1 is the first vertex, 1 plus N is the type 2 of the first vertex, 2 is the second vertex, 2 plus N is the type 2 of the second vertex, like that. So there is H from type 1 of U vertex and type 2 of V vertex with capacity 1. And it's similar to the before earlier problem. I just trained the fault Fulkerson algorithm. That is a BFS. It's the same as the earlier implementation, and this is a fault Fulkerson implementation. This is also same as the earlier implementation. So I initialized a parent array. I initialized max flow with 0 until there is a augmenting path written by this BFS. I will mark the bottleneck capacity. I initialize my bottleneck capacity is infinite, and I'll backtrack all the augmenting edges, and I'll find out which is the bottleneck edge, and I will increment the flow value with that particular bottleneck value, and I will update the edge capacities as well as residual edge capacities, and I will do repetitively until there is no augmenting path, right? And now if the value of flow, that means the value of maximum matching is at least n minus k, then I will print yes, else I'll print no. So any doubt in this particular implementation? So this particular flow algorithm is same as the earlier one. The difference in this and the earlier problem was the construction of the new graph. So basically you need to run the flow algorithm on a new graph G prime. So any doubt?
No, sir.
Perfect. So yeah, that was all for today's live session. So we discussed both week 8 and week 9 problem, in which week 8 was the simple problem because we just wanted you to get handy with the implementation of flow algorithm. And week 9 was there to because like in flow algorithms, the main thing is to come up with the flow structure. So week 9 problem was basically to know how you are comfortable with coming up with a flow structure. Then the implementation parts is simple. Right? Yeah, so if there are any doubts from both of the discussed problems, you can ask me. I'll be right here for 2 to 3 minutes. Or if there are no doubts, you're free to leave.
Thank you, sir.
Thank you. Yes, I think we can end the today's meeting link now. So assume there are no doubts, Aditya and Avi. Okay, Aditya, you are still here. Do you have any queries? Okay.